All right. Well,
Hello everyone. It's my pleasure to give you a talk about our work on the Flamingo simulations. I'll thank the organizers first to suggest that we give a talk. So I'm talking here on behalf of the Flamingo team, and I'll give you a quick tour of what we have been doing, the motivation for our simulation, and maybe some results, and hopefully that will also entice you into getting interested in our simulations, and maybe you can find something that could be useful for your own research. So maybe before we start, I just want to introduce myself. So I'm Matthieu Schaller. I'm a lecturer in numerical cosmology at the Lawrence Institute and Leiden Observatory, jointly in Leiden in the Netherlands. And the main focus of my research is to work on development of simulation software and then large-scale structure simulation, cosmology, effect of baryons and feedback, and also a galaxy formation theory. And maybe one of the main tools that I've been developing with my group mainly is the Swift simulation code, which is the workhorse behind the Flamingo simulation. So before digging into the cosmology aspect, I just want to highlight some of the things we have done in the past. And so the Swift simulation code is an open source software designed to solve large-scale structure, cosmology, gravity, subgrid models for galaxy formation, and so on. And it has been used for many different applications. The code is entirely open source, it's relatively well documented. And also, and what I mean by open source is that it also comes with all of the modeling and all of the subgrid and all of the galaxy formation model as part of the package. And everything is free, everything is there, and everyone is very welcome to make use of the software. So you have a link at the bottom here. And if you prefer reading this in the form of a paper, we had a big code release last about a year ago, and a lot of the in and out and of the development and the algorithms are all described in this paper. And so this is the tool. It's one of the main features of the code, besides its open source nature, is that it's able to run and scale extremely well on very large machines, which is also what allowed us to run the Flamingo simulations, because they contain some of the largest runs ever done down to redshift 0, which contain hydrodynamics and so on. So that was sort of introduction. So feel free to make use of any of this. But so let me now maybe come back to the main focus of this talk, which is to discuss the Flamingo simulation. And we'll start maybe a bit with a bit of motivation to bring us towards why we're doing this, some of the design choices we made, and maybe it will inspire you to see what the simulations are good for and how you can use them in your own research. So I think I don't have to really mention any of this, but just to get the ball rolling. There's a question out there whether there are any cosmological tensions between some of the probes. There's of course a famous H0 tension. Another one that gets people interested is maybe the sigma 8 tension or the S8 tension, which is, for instance, symbolized here on this figure taken from the DES release paper, where you have a difference between what the Planck analysis finds and what some of the weak lensing late time probe this measure for the omega matter S8 in the omega matter S8 plane. And maybe another way to think about it is that there's maybe a difference between early universe measurements, focusing on the CMB and or this era of the universe, and maybe more like present day measurements, which measure the distribution of matter at late time in the evolution of the universe. So, and maybe another way, again, another way of thinking about this, it might be this early universe measurement actually model dependent. So this is the lambda CDM fits to some of the early universe data, whereas maybe the late time universe is maybe a more direct measurement, less model assumption, but it might also be maybe limited by systematics and maybe limited by statistics, at least in the present day. And so maybe there are some tensions, maybe not, and that is of course one of the big question that will be answered in the next few years when we have more and more data. And what I mean by more data, if for instance would be thinking about the Euclid mission. So just as an example of many of these stage 4 cosmology probes, but directly related to the S8 tension from before, especially in the weak lensing side of things. We can just look at what Euclid aims to achieve. So, for instance, one of the exercises to constrain the nature of dark matter, in particular by measuring halo substructures, maybe also achieve 1% accuracy in the dark energy model parameters, and then also constrain the sum of the neutron masses and the structure of the mass hierarchy. So these are ambitious goals. They are going to bring, they are going to, if we can control all the statistics and the systematics, they're going to bring some very interesting answers, or going to bring some new questions. Maybe that's even more interesting. Maybe bring new questions about the nature of the physics model we assume for cosmological evolution of our universe. So one of the difficulty, though, with all of this analysis, if you think about, for instance, lensing analysis or weak lensing analysis and so on, is that a lot of the information that is being captured is actually in the nonlinear scales. So think about early universe or very large-scale structure measurements. We understand this very well. We can understand this via linear theory. We can understand this via analytic arguments. But if we now look at the late-time universe, gravitational collapse actually brings some of the information down to smaller and smaller scales, which are also the scales that we want to probe, but also the scales which can get much more complicated due to the mixture of all kinds of physics, including astrophysics nuisance parameters, for instance, due to galaxy formation. So the power spectrum on the right, for instance, the bottom right, I'm sure everybody is familiar with this, but there'll be some figures of power spectra in the rest of the talk. So I'm just setting the stage. So what you have here is a wave number on the x-axis. So this is the scale, the measure. So large scales are on the left, small scales are on the right, and then the amplitude of this is, you can think of this being the Fourier transform of the matter density field. And the data points are a collection of measurements from different scales and from different type of probes. So just to set the stage. Now, how do we think about, how are these survey directly obtaining some data? So you have someone, buys you a satellite. You're going to make an exquisite measurement of the entire sky or part of the sky or of your favorite region. But then we need to extract some information. What you will need is you have a range of models that you will be able to compare your data to. So what is very important that you have a large deck of all possible models or possible you can confront to the data. And these, depending on what you're doing, could be constructed from perturbation theory, or maybe a semi-analytic model, or from simulations, or from emulators, or from a combination of those. And then by confronting these models to your data, you will be able to extract a cosmology plot like the one I showed before, by sort of averaging or like marginalizing or making some data inference based on these models you have. Now, of course, the crucial part here is that you need to have in your deck of models or in your deck of simulations something that looks like the real universe. If you're missing a crucial piece of physics, you're either not being able to reproduce the data you observe, or you are going to infer the wrong cosmology because you're going to pick something that looks like the real universe, but for the wrong reason, because you're missing some physics. For instance, if you're missing the physics of galaxy formation, you may be mistaken about the nature of dark energy or the nature of dark matter or some other of the key parameters just because the baryons have a back reaction onto the dark matter field. So it is very important to have a very wide encompassing set of models that are used for the data inference. And so this is where cosmological simulations enter, and that's where also we enter with the FLAMINGO simulation, is of course that we want to test some different models and different theories. So we start from the top left. So we start from the very early universe where everything is linear, or quasi-linear, everything is relatively straightforward to compute. And we'll bring everything, this information down to the present day where everything is highly nonlinear. But that depends, of course, on the theory that you adapt on the way. And that's exactly what you want to test. We want to be able to generate models with different models. Are we testing lambda CDM, or maybe a modified gravity, or maybe a different nature of dark matter? Maybe you need to include massive neutrinos, or all kinds of other effects. And of course, this becomes increasingly more difficult the smaller scales you go to. And so that's where you rather teach your computer to solve these equations, and the computer solves the equations for you rather than you having to solve them via perturbation theory, for instance. And in an ideal world, as I said before, someone buys you a satellite and you can confront all of your virtual universes to the real one and infer what cosmological model we do actually live in. So maybe let me show you one of these simulations. So this is taken here from the Eagle project, which was run about 10 years ago. What you're seeing here is the gas. The intensity of the color shows you the density, and the temperature goes from dark red to white, which could be very, very hot. So maybe 10 to the 8 Kelvin and so on. And so what you can see with the redshift shown on the bottom left, and here we are just rotating around an interesting region in the simulation, is that you form this large-scale structure, you form the cosmic web as expected, and in the knots of the cosmic web, you're forming halos in which galaxies will reside. And then what is important to notice here is that around these nodes, we see these large bubbles. So we see here some material coming out of these nodes and expanding into the filaments and the void regions around the halos, right? So, and this is exactly one of the nuisance parameter we are in need to understand, right? If you're only considering gravity as the only force of nature, then everything should just collapse onto smaller and smaller and smaller scales. And so information just travels onto smaller and smaller scales, and there is no need to worry about too many phenomena. But here, galaxy formation, and here in particular, what we see, this bubble are mostly generated by some form of AGN feedback, are pushing matter back out of the halos where it comes from. And so it means that it has the opposite effect than gravity has. So you're actually propagating stuff on larger scales rather than only going towards the smaller scales. And so we really need to understand this sort of back reaction to, if we are going to actually measure the density field and try to infer cosmology of the density fields on the similar scales as these bubbles, this is really a phenomenon we need to be able to understand precisely to infer the correct cosmological model. So maybe a movie is a bit too much to see all of these details. So here's maybe a more direct picture. This again taken from the Eagle simulation. And what you have here on the left and on the right is the same region. Right? It's 25 megaparsec region, just a slice of the total matter field. So dark matter plus gas. On the left, the simulation, the universe was evolved with only gravity as a force, and on the right with what we consider a full physics model. So this includes gas physics, but also galaxy formation processes. So what you can see when you look at both images, that on the larger scales, everything is similar. You form halos at the same places, you form filaments at the same places, and you have voids at the same places. So if you only focus on large scales, or if like me, you have bad eyesight, then both pictures look exactly the same. Right? But if you now start looking at smaller and smaller scales, you can see that the picture on the right looks a lot more fluffy, maybe for lack of a better terminology, and you can see that everything looks the structure is quite different, right? You can see that there are bubbles that you can clearly be seen in a total matter field. The filaments look slightly thicker, and so on. And so this is exactly the kind of this is just a 2D slice showing exactly what was in the movie, but it's exactly this kind of phenomenon that we need to understand if we are to measure the real universe, right? So the pink circle on the scale here is a circle of about 1 megaparsec. So if you're going to measure information on scales of 1 megaparsec, which is definitely a target for something like Euclid, if you're going to filter the matter field on such a scale, you will clearly see differences between the left and the right picture here. And so you really need to be able to take into account the effect of baryons on the matter field. Otherwise, you're going to get fooled into inferring the wrong cosmology from this data. Now, the tricky part is that this is based only on a single model, and it doesn't stand that the model that was used for the simulation here, the Eagle model, is the correct model of representing the universe. So there's a large uncertainty here in how galaxy formation works and what the effect of galaxy formation models is on the large-scale structure. Let me give you an example. So this is a movie taken from Francisco Velasquez Navarro in the Flatiron, which they have released as part of the CAMELS project. So the CAMELS project is running similar simulations, similar regions of the universe with different galaxy formation models from different groups. And so here you have 6 panels from 6 different simulation groups. The one I showed you before is the Eagle model, is the one at the bottom. You've probably heard of the Illustris model in the top left. Then you have the SIMBA model at the top and some other models that are commonly used in literature. So here's the same region of universe that is being simulated. The same color scheme is used for all 6 models, and you will see the level of differences we find. So you can see this is the redshift is shown in the center. The model on the top right is close to the Horizon AGN model. It's an early riser, already at early universe. You can see bubbles forming with hot gas very rapidly. You can see later the Eagle model at the bottom sort of waking up, and then some of the other models that are really starting late. But some of them are really very late. They're late boomers, but then they really go for it, right? If you look at the SIMBA model at the top, very quickly the universe is filled with a lot of red gas. Here, red color and white color, which is like a lot of hot gas filling essentially the entirety of the universe. Right. So now, especially if you looked at the Eagle model I showed before, it was one of the weakest ones of the lot. And so maybe the bubbles that you saw in the previous pictures were actually small compared to what nature does. And maybe I should add here that these models are not just random models. They are models that actually produce a reasonable looking galaxy population in all 6 cases, right? So this is really part of the uncertainty on galaxy formation, and these are not complete outliers. So there's still a lot of variation, a lot of things we don't understand at the level of astrophysics that to really make robust predictions about what is going on. So really, we need to make progress probably in a different way. So maybe let's look at this in a more quantitative way rather than just looking at images. What I'm showing you here is again power spectra. So what you have is again on the x-axis you have the scale, large scales on the left, small scales on the right. And on the y-axis, what is shown here is the power spectrum dividing essentially the full physics model by the dark matter only model. So if you remember the 2 minutes ago, I showed you these 2 images with the left being gravity only and the right being full physics model. So you take the density field in both of them, you Fourier transform it, and you take the ratio of the 2. So this is the ratio of the right plot, which had the full physics divided by the gravity only model. Right? And this is essentially showing a deviation from a gravity only prediction. And why are we doing this? Is because gravity only predictions are very easy to generate. It's a very, these days, there are many groups in the world can produce exquisitely precise simulation, including gravity only, for all kinds of cosmological model, including modified gravity and all kinds of theories. But including the effect of baryons is what we're interested in, is actually a lot more difficult. Anyway, what we find here is that these different models, so here some are from the previous video and some are taken from elsewhere, and it's from a paper from Marcel van Dalen. What you have is the ratio of these 2 power spectra. And what is clear is that on a large range of scales, all of these models predict a difference much larger than 1%. And 1% is maybe a target for the current stage 4 missions. Actually, at some scale, you can see that it deviates at almost more than 10% compared to just a gravity-only simulation, especially on scales of about 1 megaparsec, which was the scale, or sort of the scale of interest for current probes. So what we see here is that we have models that differ immensely in their prediction, but all of them show a significant impact on the scales that we care about for future missions. So one solution about this is to do scale cuts, and this is, for instance, an example from the sort of recent pre-Euclid type of survey. So here just showing the correlation function, but the same is done in weak lensing. So this is from the DES collaboration. What they show you here is the correlation function of galaxies in different redshift bins. You have the data in black, the black points, and then you have a fit or lambda CDM fit to these points. We can debate at length whether this is a good fit or not, but this is the best fit to this data. But what is more interesting for the purpose of this talk is what happens in the gray band. In the gray band, this is the smallest scales here. And it's actually the data that was removed because it could be polluted by baryon physics. This is sort of a scale cut, only the large scales are being considered in this data. And so this is, of course, a very valid way of going about this problem, saying we're just going to ignore the regions which are problematic. But the problem is that with modern survey, like Euclid, you will add mostly points towards the left, Well, there will be some points to the right because the sky is still not entirely covered, but there will be mostly points and more precise points towards the left of here. And so you will have to do something. You can't just keep extending the gray band forever onto smaller and smaller scales. Otherwise, you'll be losing most of your data. So what are better solutions to this? Of course, this is what is adopted by currently by different collaborations, is to apply corrections to the gravity-only simulations. So you have multiple ways of doing this. One is, for instance, these models called baryonification. You also have halo models that can be used to sort of take a prediction from a gravity-only simulation, this dark matter-only simulation, and then correct for the effect in an empirical way to sort of apply a correction and sort of include the effect of baryons without actually having to simulate the whole thing. Now, this is good, but there are some built-in assumptions here, which may or may not be important. We don't really know. But one of the assumptions, for instance, that baryon effects, they are decoupled from the cosmology. So you're going to apply the same baryonification or the same halo model to all kinds of cosmological models that you're actually trying to probe. Are we talking about, so for instance, for some cases, it might be safe, but maybe if you're changing the laws of gravity or if you're changing the nature of dark matter, you may have to worry about whether some of this decoupling is actually doable or actually a reasonable assumption. Our approach, instead of that, is to actually run simulations that match the relevant data, and I'll come back to this in a minute, in large volumes to be representative, with high enough resolution to produce relevant catalogs, and that also sufficiently broad in their baryon model, so they cover all reasonable baryon feedback responses. And just as an interlude, this topic of trying to constrain the baryon physics is very important and has been also attacked from a different angle. So it's just an example here from Amon and Estafiou, where what they did is to say, okay, if I assume a Planck universe, but I want to match, say, the weak lensing low redshift data from kids, what kind of baryon model do I need? And they achieve something like the black curve on this plot. So again, here's the ratio of power spectra as a function of scale. And they find that they need a baryon model, which is more extreme than anything that is present in the simulations. So that is at least showing that maybe the data itself can start to constrain some of these models, but also it seems that we can translate a cosmology problem into an astrophysics problem here, saying, can you construct a simulation model that is as extreme as the data seems to want? Another example of this is also from the Arico group, where they also attempted to measure some property of the model, which is sort of telling you at what mass did half of the halos. At what mass did halos lose half of their gas in terms of feedback? So it would be a simple one parameter model. The model is a lot more complex, but here's just one of the parameters saying if halos are going to expel gas, and this is the way this is the main feature of feedback. What is the mass scale at which halos have lost half of the gas? And then you can translate this again into one of these baryon, this power spectrum ratio from the baryon effect, which there is their gray band, and again compared to a bunch of simulation for the literature. So here, based on this data, the feedback needs that they have is less extreme than the analysis from the previous paper. But again, this is just to show you that this is sort of the same spirit. We are trying to use some data, some external data, to constrain the effects of baryons on the power spectrum. So recently there was also some work on by the DES collaboration on using the KSZ signal to achieve sort of similar constraints on the power spectrum, and especially on the baryon physics, to then put constraint on the possible baryon response and then on a power spectrum. Okay, so I told you before, we have all of these models, so we have to pick one, and we can ask who is right among all of these lines, and then we need to design simulations around something. And so that seems like an impossible task to pick all of these different models and decide which one is right. In this work from Marcel, what he then tried to do is, can he relate some of this deviation to some observable? Again, same spirit that what was shown in the data before. So what he did is that let's pick a scale. So let's say a specific scale K. And then can we plot the deviation? So can we plot the deviation from the dark matter only simulation, so the value of the y-axis of this plot as a function of something. And so what he found, so picking here an example of taking a scale of k of 0.5, what he found is that actually for all of these models shown in the previous plot, if I plot them as a function of the baryon fraction in clusters of 10 to the 14 solar masses, all of these models sort of land on a 1D manifold, so they just land up on this curve. And he also showed that if you take different scale k, you can just get, you can actually, they all end up on, so for every single scale k of interest, you find that models line on a single manifold. And you can always express this as a function of the baryon fraction in groups, right? So the baryon effect here on the left, which is unknown, can be related to something that is observable, at least hopefully observable here in X-ray possibly. So it is a possible roadmap, and this is roadmap we adopted, is to measure the baryon fraction as a function of cluster mass. Then we can design subgrid models that are going to match this. We can run large simulations where we vary the cosmology, build an emulator for inference. Then from there, we can infer cosmological parameters from the data using the emulator. So we have a large network of models that can be used to infer cosmology. And as part of this emulator, we can also vary the baryonic response around our best guess. And the best guess is taken from the previous information, saying, if I can understand the baryon fraction in clusters, I can understand the baryonic response. So that is the premise of the design of the FLAMINGO suite of simulations. So here's our approach. So let's first just have a title advertisement slide. So the FLAMINGO project is just it's a collaboration between Leiden, Liverpool, and Durham. There's a range of people here with the Leiden crowd and the line. And for those of you familiar with the simulation literature, it's actually sort of a successor to the Bahamas project. So it's similar spirit. It's a much larger volume with a newer code and a newer design of the subgrid models. And really, we want it to be thought of as a virtual twin to late-time cosmology probes. So think of Euclid, SPT third generation, Rosita, Simon's Observatory, and so on would be a sort of real-life counterpart to the model we are producing here. So the basics of these models, so it's a series of boxes and resolution going from 1 gigaparsec to 5.5 gigaparsec, and the gas resolution is 10 to the 8, 10 to the 10 solar masses, so it's actually relatively low resolution, right? A Milky Way galaxy will be sampled with 10 to maybe 100 or 1,000 star particles. This is very little, but this is also not the goal of this simulation. The goal is not to reproduce galaxy formation properties. The goal is to have an effective model that reproduces the gas fraction of clusters such that we get the correct response on large-scale structure. These were run with the Swift code, which I introduced at the very start. And maybe what is two features which are interesting at this stage, that we have particle-based neutrinos, and we have machine-learned calibrated subgrid models. And I'm coming back to these two specific things in a minute. And the main run we did is a 2.8 gigaparsec box with 5,000 cube gas particles, the same number of dark matter, and also about 3,000 cube neutrino particles, with a fiducial DES plus all external cosmology. And this simulation box is actually the largest hydrodynamical simulation run to Redshift 0. And it comes along with a series of other boxes where we vary either the cosmology or the galaxy formation. So it's just an example of an image, a map you can make of this simulation. You've probably seen many of these large-scale structure, filamentary structure images from simulations. What you may not have seen, though, is the coloring that we used here. So you can see the filaments in the dark matter and so on, but the coloring in yellow and blue on top, this is showing you the density of the neutrino field. Right? So the neutrinos are very light, but do actually cluster a bit, and that may matter or not for precision cosmology, especially if for higher neutrino masses. That's a feature which is sort of also new, but something we can do with our simulation, which is not commonly done. And so for fun here, I've highlighted the region at the top, just one of the biggest clusters in the simulation. And we can zoom in. So here's a 400 megaparsec on the side cut out. Sorry, 200 megaparsec on the side cut out of this region. And I can zoom in. So here showing the gas temperature. We can zoom in again and look at the dark matter structure around this cluster now in a 50 megaparsec zoom in. Then finally, what we can do is that we can produce also mock X-ray maps. And so here is just in one of the two E Rosetta bands, the surface brightness in this region. So we can do this for all of the tens of thousands of halos we have in a simulation, which allow us then to compare directly to X-ray survey, for instance. Some key ingredients I mentioned before, we're using the Swift code. We have massive neutrinos. We use state-of-the-art multi-fluid initial conditions that can treat perfectly the dark matter and the gas and the neutrinos separately and produce the correct transfer functions. In terms of subgrid physics, I don't want to go into the details here, but we have the usual type of models. We have radiative cooling, star formation, enrichment from stars, supernova feedback, and various models for aging feedback, which I'm going to mention in a minute. But what is more interesting about a subgrid model is what was done to calibrate the model. So what is traditionally done is that you pick a set of observables that you think are relevant. So here on the left, you have, for instance, the stellar mass function, the black point, so the number of stars per unit, sorry, the number of galaxies per unit volume as a function of the stellar mass of the galaxy along the x-axis. And on the right set of plots, what you have here is the cluster gas fraction. So you have a function of cluster mass on the x-axis, you have the gas fraction on the y-axis. And I argued before that there is this relationship that in the Van Dalen paper showing that the cluster gas fraction is an important proxy for the baryonic response. So what Roy Kugel here, that led the calibration effort, has done, he took two of the parameters of the model and then just played around and showed that if you change these parameters of the model, so there's one on the top related to the black hole accretion, the bottom is sort of a black hole feedback, and there are many other parameters you can play with, but you can show here that you can move around the model, so the different curves are different models, they can move around and get around the data, right? And so, for instance, the bottom parameter has a big effect on the cluster gas fraction, but the top parameter has more of an effect on the stellar mass function. And so what he then did is that he ran a series of 50 models, varying all kinds of parameters at the same time, to which he built an emulator and then asked the emulator, so a simple Gaussian process emulator here was sufficient actually to cover the complexity of the model. You can ask the emulator, please find me a model that goes through the data points on the left and on the right at the same time. And so this is just a corner plot showing you that we can achieve, we can very well constrain these parameters. And because we are playing with the data, we can also fit for additional things like observational biases like cosmic variance and so on. And so we can actually construct a model here where that fits the data as well as we like. And here's an example, a different resolution. So again, showing the two same data sets that we think are important. The black points is the data. The light blue curve is an emulator telling us, here is the best I can do given the model you have. And in red is then if you go and actually run a simulation at the point the emulator tells you, and you get exactly what you wanted. So you get a very good fit to the data as demanded, right? So we can construct models that have both the correct stellar mass function, which is important if you're going to get something like clustering of galaxies right, and at the same time we can get the gas fraction in groups and clusters as demanded by the data. And here it's mostly X-ray data that is being used, X-ray and weak lensing masses. So I could show you many plots, but what we can also, so we're also running at 3 different resolutions, which also means we can run at very different box sizes, which allows us to construct different kind of observables. But you can see the, for instance, in this single region, at least visually, that we can get a nice convergence. We get the same large-scale structure and the same objects at resolution that differ by 2 orders of magnitude here. We also get in this big model, in this big simulation, that now that we have constructed the model we like, Joey Bradmaning showed that we actually reproduce a lot of cluster scaling relations very well. For instance, you have temperature versus X-ray temperature versus X-ray luminosity on the top left. You have also some nice properties with the SZ brightness bottom as a function of mass, or you have the temperature as a function of mass on the bottom right, and so on. So you can look at this paper for all kinds of relation. Essentially, our fiducial model, as predicted by the emulator best fit model, is actually produce a lot of the data sets extremely well, at least in the X-ray, which is exactly what it was designed to do. Joey also showed in his paper that the profiles, not just the total quantity, but also the profiles of these clusters are actually matching very well with the data. Now, if you only have one model, you're not going to be able to do much inference on the cosmology, especially if you're baryon physics. So what we can do, which is part of sort of novel in our approach, is to be able to vary the model in a systematic and controlled way. So now we have an emulator. What I can do, instead of asking the emulator to give me the best fit to the data, that I could shift the data by 1 or 2 sigma and ask the emulator, give me a model that reproduces that shifted data. So if you focus here on the right plot and you look at the blue curves, there are essentially variations where we shifted the data points by 2 sigma in one direction or 2, 4, 8 sigma in the other direction. And then we ask the emulator to generate a set of with astrophysics parameters such that we go through these points. And so we can then we can run a simulation exactly where the emulator predicts, and we obtain the gas fractions that we see on the right here. So you can see from light blue to dark blue, we can really control the gas fraction and get models that respond as we want. We can do the same thing for the stellar mass function. So if you look on the left, we can get the orange curve is a shifted stellar mass function where we shifted all of the stellar masses by 1 sigma to the left. At the same time, we can do this without changing the gas fractions. We can shift them independently. What we can do additionally is that we can change completely the AGN model and say, oh, but maybe AGN, which is the main driver of all of the effects we see, at least in our model, by having them having more directional jet-like behavior. And then that actually would be the green curves that we see here. So we can again produce models that reproduce the data or reproduces the shifted data, but now is a different way of injecting energy, because maybe that will allow us to see a different behavior in some of the results we have. And finally, maybe one thing which also is interesting from the simulation is that the very large data sets, but we also produce for the main simulation, we have 8 different independent observers in the simulation that produces a light cone, where we produce data on the fly for X-ray in 6 different bands. We also have Sinuev-Zeldovich effect, dispersion measure, mass maps from which we can do weak lensing and stellar light and so on. And we actually have a very fine 13 arc-second pixel, so we can do full sky maps on all of these quantities that we can directly compare to data. So for instance, here's a Compton Y map, which could directly be fed into an ACT or an SPT type pipeline and see whether we recover the same information or whether we can understand differences between data and simulations. Let me finish maybe with some results before inviting you to join us. So maybe the most basic thing we can first look at is just the halo mass function. And this is not very interesting. This has been done many, many times, but I wanted to highlight here especially. So you have halo mass on the x-axis and you have the number of halos per unit volume on the y-axis. But the right axis here shows you the number of halos per small bin in the main simulation. And so if you are interested in clusters or in cluster cosmology, you can see that we have tens of thousands of objects, or maybe more than 100,000 objects above 10 to the 14 solar masses. Right? So if this is something you're interested in, we have a lot of data that can be very useful in this respect. We can compare this to like published halo mass functions. We see small differences at the 5 to 10% levels, especially if you look at the plot on the left. If you compare to, for instance, the Tinker or the Mira Titan emulators, we see small differences. And this is quite interesting. Some of it comes from just definition of halos or halo finders, and it sort of can get very technical very quickly. But it's also interesting to see that even at the theory level, at the community level, we don't necessarily agree on just basic prediction like the halo masses in a gravity-only simulation here, but it would get more complicated if you added the baryons. So maybe that's something for us theorists to sort out in the near future. If you throw in gas physics, here's what we get. So this is now showing the ratio of the simulation with baryons divided by the dark matter only mass function that we all know and love. And so the function of halo mass, you can see the effect here on the y-axis, and you see that in clusters or so in small groups between 10 to the 13 and 10 to the 14, we see almost a 20% drop in the halo mass function. And what is also interesting is this is exactly modulated by this model. So if we change the gas fraction in clusters, so if we change the intensity of feedback, we can move this curve up and down. Coming back to the power spectrum, which was one of our key goals in the first place, is just again showing as a function of wave number, the effect on the power spectrum as a function of scale between hydro and dark matter only. Especially if you focus on the blue and red curve, these are our two high resolution model. The yellow one is very low resolution. We see this is our predicted effect of baryons. The dark gray band is a 1% range, the lighter gray is a 5% range, and you can compare it here to two different models from the Bahamas and the Millennium TNG simulation. But again, what is more interesting is if you start varying the baryon physics, and I announced at the start or a bit earlier that we're going to be able to modulate this based on the gas fraction clusters. And so if I change the gas fraction clusters based on observation, I indeed here can modulate the baryon effect on the matter power spectrum as predicted. Right? I can move it up and down, I can move it left to right as a function of the gas fraction. So it's a function of an observable. And I can play the same game with the other variations, but here the separation is less clear. But we can still characterize our uncertainty. So essentially, if you tell me in the data what is the gas fraction in clusters based on X-ray, I can tell you what the baryonic response is. And if you tell me, oh, I'd like to have an error bar around that because I'd like to put this in my emulator for cosmology inference, well, here's the left plot. We have that information that is available, and we can modulate it as a function of an observable, which is the key part. What is quite interesting as well is that Willem Elbers look at whether this correction, so if you take the fiducial model here in green, but you now look at variations in cosmology, is the baryon effect actually factorizable, or does it depend on the cosmology itself? So what Willem did, he ran a set of simulation around the Planck-based lambda CDM model, so it's relatively well controlled and actually small variations around the Planck-based lambda CDM model. And he finds here the baryon fraction, so the baryon correction as a function of k again, for these different variations. And so he finds that for at least a reasonable range of variation, the baryon effect on the power spectrum is within 1%, up to a scale of k of 2 or 3, and so and on. But if you are interested in more precise measurements, then the assumption that the baryon effect is factorizable may not be entirely correct. There's clearly a small effect that you can see on the bottom panel here. Finally, some result on cosmology inference. So this is from a paper led by Ian McCarty. So here showing a large set of plots. I won't write too much about it. This is comparing the lengthing to the kids' data. So on the left, you have all of the tomographic bins and the cross bins are the data points. The data points are the same on the right. And what you have on the left here is what happens if I vary the lines or if I vary the baryon physics. You can see that it really doesn't have much of an effect on the fits to the data, right? Whereas if you go to the right, what you do there is that you change the cosmology. So you go from our fiducial cosmology in dark green to something like a Planck cosmology in sort of lighter green. And more, for instance, if you take an Amon and Staffew predicted best fit to kids plus baryon cosmology, this LS8 model in dark red, you can see that actually this has much more of an impact on these measurements than just baryon physics. At least with current precision of data, it seems like cosmology dominates clearly in the signal over the baryon effects. Another thing you can do with the simulations, because we have the full gas information, we can actually predict the Sunyaev-Zeldovich effect. So this is now looking at the Sunyaev-Zeldovich power spectrum, angular power spectrum. So you have a bunch of data points here on the plot from Planck and SPT, and again our fiducial model in green, and then varying the baryon fraction in clusters. We see that none of these really helps to get close to the data, but if you change cosmology instead, actually there you have much more of an impact. Of course, the SPT point is really out of reach of any of these models. But for the rest, if you only take the Planck data, actually lowering S8 helps immensely, and that's something that the baryon physics is nowhere near able to reproduce if you look at the left plot. In a similar vein, here is the effect on the TSZ cross weak lensing from kids cross Planck ACT. And so on the left, again, you have the same story where changing the baryon physics doesn't have much of an impact on moving where the line is. But if you look at the right plot, if you change cosmology, this is much more important. But what's interesting here is to see which probes are directly sensitive to baryon physics and which probes are more like directly sensitive to cosmology, and where are the probes that are affected at the level of precision that we can that we have to worry about for baryon physics, for instance. Another topic which I'm not going to discuss because Jaeger Broxteman is giving a talk on his own about the lensing peak analysis that he has done from the simulation. But of course, because we have all of these light cones, we can produce a full weak lensing map of the whole sky, to which we can apply noise and smoothing and all kinds of masks and artifacts, which is what he has been doing. So I would invite you just to have a look at his talk, where he looks at the sensitivity of weak lensing peak statistics and weak lensing peak counts, how sensitive it is to baryon physics for future probes. And so finally, to conclude, I hope I've convinced you that Flamingo and mostly the variations around the main model, they will provide a unique framework to explore the interplay between cosmology, mostly large-scale structure here, but cosmology and baryon feedback. I argue that the calibration strategy we use leads to a reasonable prior on the baryon effect. So we have a good prior for the mean model, but also we have a prior and an interesting range of variations, which is data-driven and data-related. We can use directly raw quantities like halo masses or power spectra can be explored, but also because we have all these virtual observers, including survey characteristics, survey noise, smoothing, and so on, this can all be used and can all be done, and you're all welcome to join this. And of course, the data set is immense. The entirety of the data is about 8 petabytes. It's all kinds of different simulations, variations in cosmology, variations in astrophysics, baryon effect. And you're all very welcome to get in touch and use the simulation for your analysis. And yeah, if you're interested, I'll be very happy to answer your questions or see how we can help you making use of the data for your own research and so on and so forth. So thank you very much, and I look forward to the discussion session about this and all of the rest of your work.